Okay, so today let's present briefly the second important public key crypto system in this class, namely Diffie Hellman key exchange. Okay, so before starting, let's get some preliminary information background about primitive roots modulo primes. So what is a G? Let's write down a definition. G is a primitive root modulo of prime P if the powers of G cover everything that is non-zero modulo P. So if the set consists of G the power 1, G the power 2, all the way through G the power P minus 1. So because here at this moment G the power P minus 1 gives the Euler's theorem in the form of Fermat-Little theorem. This is 1 in ZP. So if we continue multiply G to the power 1 by G, we get G squared, G cubed to the power 4, and so on, G to the power P minus 1. G to the power P is back to G, so we don't get anything more after this. So this set consists, is equal to the set of all powers, all positive elements modulo P. So 1, 2, up to P minus 1. Let's have an example. These are two examples. One example in which an element G is a primitive root, and another example in which G is not a primitive root. Let's see, P equals to 7, G equals to 3. So let's try to look at the powers of G. So let's make a brief table N versus G to the power N, not G, in this case 3 to the power N mod 7. So 3 to the power 1 is 3. So at every step, multiply the previous entry by 3. 3 times 3 is 9. So mod 7 is 2. 3 times 2 is 6. 3 times 6 is 18, but mod 7 is 4. Because 18 is 14 plus 4, and 14 is 0. 3 times 4 is 12. Because 12 equals to 7 plus 5, and 7 is 0. Okay. And 3 times 5 is 15, and again 15 is 14 plus 1, but 14 mod 7 is 0, so we got 1 here. So as we see, the powers of 3 cover all non-zero elements modulo 7. So 3 is a primitive root. Mod 7. On the other hand, there's the example 2 of an element that is not a primitive root. And there is another reason. Example 2, the number 2, proceed P equals to 7, but in this case 2 is not a primitive root. In other words, so there is a power of 2 of a non-zero element in ZP that is 1, that means the 6th power. So the problem with the primitive roots is that we don't want to get 1 earlier than 6. So look at 3 here. The first time that positive power of 3 is 1 is the 6th power, which is P minus 1, 7 minus 1. For 2, let's see. 2 to the power 1 equals to 2. 2 to the power 2 equals to 4. And 2 to the power 3 equals to 4 times 2 is 8. Now this 8 is 1, because 8 plus 7 is 1. So we got 1 earlier than 6. So if we consider all positive powers of 2, we can only get 1, 2, and 4, nothing more. So the set of all positive powers of 2 consists of the set 1, 2, 4. So it cannot cover all non-zero elements mod 7. So 2 is not a primitive root. An important theorem, of course, every prime number has a primitive root. Right? So for the purpose of our explaining the Diffie Hellman exchange, it will be enough for us to know that every prime number is a primitive root, and there are various methods how to get a primitive root, but we'll be concerned about this later. So right now, let's start from this idea that every prime is a primitive root and explain how Diffie Hellman key exchange works. Okay, so let's see. In the Diffie Hellman key exchange, we have two communicants, as always, Alice and Bob, the good guys, let's say. So this is the home of Alice, and there's the home of Bob. Okay, so the problem is they can communicate, but the channel is not safe, so it's not secure. So they communicate over unsecured channels. So the channel of communication is represent like a wave-like pattern here. Is an unsecured channel. That means there are plenty of eavesdroppers here. So we could have, so one classical eavesdropper, the name is the Oscar, which listens to the communication, and then you can have also we can have also Eve. Right? Eve and Oscar, they see this. So there are two, impersonations of eavesdroppers. So Alice and Bob communicate, and over the channel, which is unsecure, there are plenty of potential eavesdroppers. Okay, so let's get started. So at first, Alice and Bob communicate over a totally unsecure channel, so whatever we discuss, people can hear. So over this channel. So let's see, they keep discussing and they agree on a big prime, large prime P, and a primitive root modulo P. So yes, that's a problem because everybody else knows this prime P and the primitive root G, but we'll show later that why this doesn't really matter. So Bob and Alice, in their discussions, they agree on a big prime P and a primitive root G mod P. So for practical purposes, they can make this public. So Bob, they don't even wait for the people to they simply make it public. So Bob and Alice, they discuss and choose a big prime P and a primitive root mod P. So the values of P and G are public at this moment. So Alice the same. This flag over the Alice home and the Bob's home reflect the idea that P and G are public. So P equals to whatever they agree on, G equals to whatever they agree on. At this moment, it's all set, but at this time, both Oscar and Eve, they both know P equals to and G equals to. They know this too. Right? So let's see how Alice and Bob can take advantage of this idea of a primitive root modulo P. So in her private home, Alice will select a secret number between 1 and P, which will be her secret key. So selects A between 1 and P. And Bob does something similar in his private home. he selects a Bob's private key, a number B, small b, between 1 and p. And then applying the fast exponentiation algorithm, Alice raises the primitive root g to the power small a mod p, and she calculates the number big A equals to g to the power small a mod p. And Bob does something similar. In the privacy of his home, he calculates big B equals to primitive root g to the power small b mod p. Okay, and now we have two other numbers, capital A and capital B, so which now Bob, they exchange. Bob sends capital B over to Alice, and Alice sends capital A over to Bob. So over the channel, let's see, we have this capital A going from Alice over to Bob, and capital B going from Bob over to Alice. So in this direction, there is capital A circulating like this. And then here. So Bob knows now the capital A coming from Alice. And Alice also knows these secrets in that direction over the channel. And Alice knows now capital B transmitted by Bob. Okay, what's the problem of the Oscar and Eve? So Oscar and Eve, they know P and G. And then they see A and B. So they know A and B. So the problem is, even if they know the system. So we always can assume that the eavesdroppers know the crypto system that is used. So Oscar and Eve know that Alice and Bob use the Diffie Hellman key exchange. And they know that big A equals to G the power small a mod P. And Oscar and Eve know that big B is the primitive root which they know, the power small b which they don't know, mod p. But even if Oscar and Eve know those powers, the power of g of order small a, and they know the power of g of order small b, they are unable. That's the big point of the Diffie Hellman exchange. Even if they know the power, they know they cannot take the logarithm. So this difficulty of the discrete logarithm problem is key for the security of the Diffie Hellman key exchange. So Oscar and Eve, even if they know big A and big B, due to the difficulty of the discrete logarithm problem, they cannot find small a and small b. So even they are unable to find which power of the known primitive root modulo non-prime, which is large, is a given value A. So that's the problem. That's the strength of Diffie Hellman key exchange. Now, okay, let's see what's next. So Alice receives big B from Bob. Bob receives big A from Alice. What's next? Simply, Alice calculates big B, which she receives from Bob, to the power her private code A. And Bob receives big A from Alice and calculates big A to the power small b, which only Bob knows small b, and Alice knows small a. And the theoretical motivation for the Diffie Hellman key exchange is the equality of these numbers, like a reciprocity. Big B to the power small a equals to big A to the power small b. Again, mod p. How to show this? Well, it's easy. It's like basically it's property of the exponentials. Big B is g to the power small b, right? And g to the power small b is big B to the power a is g to the power ab. The same here. The big A is g to the power small a, and g to the power small a everything to the power b again is g to the power ab. So at this moment, by doing these operations, so Alice big B to the power small a and Bob big A to the power small b, they can do this because Bob receives big A from Alice, and he raises the number that he receives from Alice to the power his private key, and Alice receives big B from Bob, and she raises B from Bob, she receives from Bob upon her private key A, those numbers are equal according to this theoretical explanation. So at this moment, Alice and Bob are in possession of a key, which is G to the power AB, which is B, capital B to the power small a, or capital A to the power small b, either one of them, that the eavesdroppers are not aware of. So that's the idea of Diffie Hellman key exchange. Now let's take let's take an example. But before this example, let's try to list some primitive rules just for people to know. There are tables, big tables of primitive rules, and they can also be done with Maple. But we'll discuss about this Maple implementation later. So from now on, we'll do everything by hand. So let's list the number of the first couple of points. We get 2, 3, 7. Okay, the primitive roots. I'm going to list here the primitive roots of those numbers. Okay, so let's see. Here. So the primitive roots are 1, 2, 2, 3, 2, 2, 3, 2, 5, 2, 3, and 2, 6, 3. So these are what are these? These are the least primitive roots modulo the corresponding primes. So for example, 5 is the smallest primitive root modulo 23, 2 is the smallest primitive root modulo 37, 6 the smallest primitive root modulo 41, and so on. Okay, so now let's try to cherry pick and this. So let's pick up the case among those primes, in case the largest primitive root to the beginning. So 6 is the primitive root modulo 41, and let's take this for to be P and G. Okay, so let's see. So say P equals to 41 and G equals to 6, which you know that 6 is the least primitive root modulo the prime P 41. Okay, so let's say that let's go. This is Alice on the left here, and here's Bob. So let's start. Alice chooses her secret key, small a equals to 11, let's say. And Bob chooses small b equals to 80. So let's see how the Diffie Hellman key exchange will unfold. So after Alice chooses her secret key A, she calculates uses fast exponentiation to calculate G, which is the primitive root 6 to the power of 11 modulo the prime P is 41. Okay, so let's do a fast expansion table, K versus 6 to the power K. By the way, everything in this example is mod 41. So I could just write mod 41 or mod what it goes out saying here. Okay, so let's see. So how does it work? So on the left column we double each time we advance, and on the right column we square modulo 41. So 1, 2, 4, and 8 here. 6 to the power 1 is 6. 6 to the power 2 is 36. Okay. 36 squared. Let's see if we can find some shortcuts. 36, because we want to work by hand. 36 is minus 5. Because if 41 is 0, then 36 minus 5. Minus 5 squared is 25. Then, let's see, 25 squared is 625. Well, let's see, 625 if you divide by 41, how many times enters 41? 62. 1 time 41 here, I get 21. Bring down the 5. How many times enters 41 into 15? 5 times. So 205. The remainder is 10. So we put a 10 here. Okay, so we want to calculate 6 to the power 11. How to get a 6 to the power 11? Let's use a greedy algorithm to write 11 as the sum of items in this the first column. So 11 equals to 8 plus 2 plus 1. So to calculate 6 to the power 11 by the law of exponentials, we have 6 to the power 8 times 6 to the power 2 times 6 to the power 1. So 6 to the power 11 equals to 6 to the power 8 times 6 to the power 2 times 6 to the power 1, because 11 is 8 plus 2 plus 1. And this will be 10 times 36 times 6. Right. So let's see. 36 is, let's see, by 10, 36 modulo 41 is minus 5. And 6 times 10 is 60. But 60 is 19. Right? Because 41 is 0. If 41 is 0, 60 is 19. So what we got here, minus 5 times 19 is minus 95. Minus 95, how to make a negative number, a negative looking number, a positive looking modulo 41. And then suitable at 41 as long as, until for the first time we get positive. So we add, so equals to minus 95 plus 123. Because 123 is 0. So it doesn't change anything, only the appearance of being positive, so in a standard form. So we'll get 28. So Alice calculates capital A by raising the primitive root of our secret key A, and she gets capital A equals to 28. So let's erase the work and keep the fruit of the work. So now we got big A is 28. So big A equals to 6 to the power 11 modulo 41 equals to 28. Okay, now let's see what Bob is doing. Bob calculates exactly like Alice, calculates the primitive root 6 to the power 18 modulo 41. So let's be big B. Okay, so again, K versus 6 to the power K modulo 41. Okay, so let's see. 1. So here we need to calculate the 18th power. So that means in the fast text table, we have to go through 16. So 1, 2, 4, 8, 16. 6 to the power 1 is 6. 6 to the power 2 is 36. So we go as before. 6 squared will be 6 to the power 4. So we got as before 25. Then we got the 10. The same thing, this part of the table we got it before. I erase it here. So 6 to the power, 6 to the power 16 is 10 squared. And 10 squared is 100. 100 modulo 41. How many times enters 41 in 100? 2 times. Then 82. 82 is 0. If 82 is 0, 100 is 18. Okay, now how to get the 6 to the power 18? 6 to the power 18. How we get an 18 as the sum of items from the column of the first column? Greedy algorithm. So 6 to the power 16 plus 2, which will be 6 to the power 16 times 6 to the power 2, which will be 18 times 36, right? Which will be 18 times minus 5, because 36 is minus 5 because 41 is 0. So this will be minus 90. Minus 90. Okay, so let's make a negative looking number positive looking. So it will be minus 90 plus minus 90. plus 123. Because 123 is 41 times 3, that means 0 mod 41, so this will be 33. Okay, so we got big B equals to 33, so that's the fruit of our work so far. This 33, and let's erase the work, and we got the fruit. Okay, so Alice gets big A is 28, Bob gets big B is 33. So Alice will send over 28 Bob. And Bob sends over 33 over to Alice. So Bob receives 28. This is marked 28 is circulating over the wire. And Alice receives 33, which circulates over the wire from Bob to Alice. So Alice receives the 33, see what Alice doing. Receives 33, and she raises 33 to the power of her private key. So Alice does the following calculation: 33 to the power 11 modulo 41. So let's see how, so let's be the commonly shared secret as seen from Alice. So again, use the table for the fast exponentiation. K versus 33 to the power K mod 41. 1, 2, 4, 8. In the left column, every step of the algorithm is double. In the right column, every step of the algorithm is square modulo 41. So 33 to the power 1 is 33. 33. Which is modulo 41. This will be minus 8. Right? Which makes the second, in the second row, we get 64. Right? 8 and, but 64 is modulo 41 is 23. In row 4, 23 squared, what is what we get here? 529, right? That's 23 squared. But modulo 41, let's see how many times enter 41 in 520 in 52. One time, so 41 here, 119 here. How many times enter 41 and 119? 2 times, right? This will be 82. 82 to 100 is 18 plus 19, 37. 37 is the remainder, so 37 here, right? Which is again minus 4, which makes 16 the number here. Okay, so let's calculate the 11 power. 11 power is the 8 power times the, as before, 8 power times the second power, the first power. So if you calculate 16 times 23 times 33. Okay, so let's see. So let's see what we get here. 33 is, let's push in before this minus 8. This 16, because we are looking at mod 41, right? 16 can be, let's split 16 in 8 times 2. And then this 2 times 23, it's a 46, that will be a 5. Then 8 times 5 is a 40, that will be a minus 1. Right? And then finally, minus 1, which is minus 8, is 8. Let's what can we do? One possibility if you want to go by hand. So the commonly shared secret as seen from the Alice side is 8. That was the word, and now let's keep the fruit. So 8 is the commonly shared, the shared secret. Negotiated over an unsecure channel. So okay, so this Alice is work. Now what's Bob doing? Bob receives capital A, which is 28 from Alice, and he raises 28 to his secret key 18. So he calculates 28 to the power 18 modulo 41. Again, let's make the fast exponentiation table K versus 28 to the power k mod 41. So as before, we need to go until 16. Right? 1, 2, 4, 8, 16. Okay, so let's see. Okay, so it's now 28 on the first row. 28 squared. How to do it faster? 28 is, let's see, there's a square paper. 28 equals to minus 13, right? 13 squared, minus 13 squared is 169, right? 169, how many times enters 41 in 169? Is 164, which is 0, plus 5, because 164 is 41 times 4. So that is 0. So 28 squared is 5. Right. 5 squared, 25. 25 squared, we did it before, I don't recall exactly. So 525, 1 times 41 here, and then 5 times, that will be a 10. And finally, 10 squared. 10 squared is 100, but mod 41 is 18. Okay, now there's the table. Now let's write down the exponent, the second step of the first exponentiation. So 28 to the power 18 is 28 to the power 16, which you know from the table, times 28 squared, which you know from the table. That will be 18 times 5. 18 times 5 equals to 90. And 90, but everything is mod 41, right? 90 mod 41 is 8, because 82 is 0 mod 41, which makes 90 to be 8. So, Bob calculates 20, is summarized here. Bob calculates 28 to the power, the code he receives from Alice, A, right, capital A, and he, after this fast exponentiation, he gets the same number 8. So, this would be 8 again. Let's erase the mod. See what is that overall. So Bob is a secret key 18. So he takes the primitive root, raises to the power his secret key, he gets big B, sends it over to Alice. Alice receives big B, which is 33, and she raises 33 to the power her secret key modulo 41 and gets 8. And Bob does the same. Bob receives the capital A from Alice and raises the information he gets from Alice in the power his secret key and gets the same number 8. So at this moment, this number 8 plays the role of the shared secret between Alice and Bob that was negotiated and agreed on over an unsecured channel. So common shared secret. So there's an idea, a very nice idea that shows us how can we still keep our privacy / secrecy even if we communicate over unsecured channel. At least as long as the discrete locality problem is for all practical purposes, at least for big primes P, interactable. So that, in summary, is the idea of the Diffie Hellman exchange.